All right, well, I will begin with a word of prayer once I get up here. Dear Father, we thank you for this day. Again, I thank you for this class, and just ask you to give us wisdom today, help us to understand the Dirac delta function and how to use it, and just to give us wisdom on how to understand the Laplace transform method. And again, we just pray that you be glorified in what we do, Lord. In your name I pray, Lord Jesus. Amen. All right. Get some lighting in here. Come on. You can do it. All right, there we go. So, I got you guys something, which is the exciting, although I don't like the way this is copied, so it's not great, but something like this I will hope to provide for you. I'm hoping to like type this thing up so it's better. It's something I've been meaning to do for a number of semesters, and I just keep forgetting. It's like take one and pass it back. Thanks. But you are allowed to have this sheet or its improvement on the next test. So like you don't have to memorize everything Laplace transform wise, but you do really want to familiarize yourself with all of the results here and how they work, right? But for the next test, I'll allow you this page, whatever it becomes, as well as whatever else you can write on it. So you could write, like whatever you want on the back of the page or whatever. So that should help you. Any questions before I go on from there? Yeah. Did I not post the solutions for mission 3 yet? Aw, man. Well, that's annoying. I had those ready like a week ago. Yes, I will try to do that. If you notice something like that, email me. And I'm more likely to do it when I get back home and stuff. But I will try to do that once I'm done with other stuff today. Mission 3. Okay, yes. Speaking of which, the grader was supposed to grade that today. All right. Well, anyway, hopefully you will get mission 3 back Thursday, if all goes as I hope. So let us talk about the Dirac delta function. A little bit weird, but don't be afraid of it. It is a necessary device. I'll put some scare quotes on this because technically speaking, it's not a function. In fact, the Dirac delta function is an example of a distribution, which is a generalization of the notion of function. And the fact that it's not a function is somewhat revealed by the fact that it has some really weird behaviors as follows. So we use delta of t is characterized by number one, we can think of delta of t basically case-wise defined. You can think of it's basically 0 for t not equal to 0, and it's infinity. If t is equal to 0. Now, what do I actually mean by that is probably better encapsulated in number 2, which is that the integral from minus infinity to infinity of f of t times delta of t dt is simply equal to f of 0 for any function f that is continuous in some neighborhood of 0. So basically, if f is continuous near enough to 0, then what's going on here? What's going on here is to say that the Dirac delta function is turning integration into evaluation. Like, let me just, before I tell you more about like what's the point of this thing and what does it model, let me just like do an example. It's bizarre, right? So like example 1, if we had the integral from minus infinity to infinity of like cosine of t squared plus 7. Let's take this cosine and let's trade it out for a cosine, the 47th power of cosine. There we go. Delta of t dt. Well, this is equal to the 47th power of cosine of 7. It's like, what? Yeah. And, you know, likewise, if I had like integral from minus infinity to infinity of, I don't know, sine cubed of t plus 10, delta of t minus 1, how does that work? What would that give you? Again, it just gives you, the only time it's non-zero is when the delta is infinity. And when it's infinity in such a way that it just evaluates this at t equals to 1. So like we just put sine cubed of 11. 1 plus 10 is 11. So let me say a little bit more here. What's going on, right, if you think of it graphically, is if we have t naught here, right, and this is, let's say we're graphing delta of t minus t naught. So what's going on here is this thing is 0, right? It's 0. It's 0 like here, and then all of a sudden when it gets to t naught, it's like this infinite spike, you know? I can't even get to the top of it, right? It's up and up and up, and I'm drawing that, you know, as if there's some thickness here, but really it just goes up and up and up, all right? And notice that the integral from like, you know, minus infinity to infinity of delta of t minus t naught dt, well, by my characterization over there, I just take the function that's multiplying the delta and evaluate it at t naught. But what's the function multiplying the delta? It's just the constant function 1, right? So this, by the definition of the delta, it just works out to 1. What does this mean? This means that this infinite spike, right? What's the deal? It's a, you know, it's like an infinite spike. Infinite spike under which the area is 1. So that's what the Dirac delta function is. It's an infinite spike that somehow the area under the spike is 1. All right, that's the construction of this delta. Now, the way this is actually constructed in terms of careful mathematics is not a single function, but actually a whole sequence of functions. You take like a whole sequence of functions, like the model of it is something more like this. Here's t naught, right? So what you're going to do is your first function maybe looks like this, right? And then the second function, maybe it looks like this, all right? And then the third function, maybe it looks like this, all right? And so forth, right? Like 1, 2, G3, right? And the limit, as n goes to infinity, of G sub n is equal to the delta. That's how it's actually implemented formally in terms of mathematics, if you want to study it. There's a mathematician by the name of Schwartz who did this junk in like the 20s or 30s or something. No one teaches it in this course if they know what's good for them. I don't either. But there is a careful mathematics underlying this theory of distributions. Now, and so the deal is every one of these sometimes they're called tent functions or something. Every one of these functions is constructed so that the area under the function is 1. And so in the limit, the area is still 1. That's the idea. But anyway, so, all right, this is already very, very weird, because you guys know one of the things we drill into your head about integration is if we throw out one point, does it change the integral? Certainly not, right? If I have an integral from 0 to 1 and I just like delete, one of the points from the integration, I don't change the area under the integral, right? Not for a function, but for a distribution, it can absolutely be the deal. Like if I delete t naught from this integration, all of a sudden it's 0, right? That's very weird behavior. It's not behavior befitting a function. What do you think? So anyway, now that we're entering this freewheeling madcap world of distributions, what's the derivative? What do you think the derivative of the unit step function at t naught is? This is a very weird thing to ask as well, because the unit step function's graph looks like what? I'll do it down here. Right? It's 0. Right? Until what? Until it's not, right? What's the derivative of the unit step function? I'm sorry, I'm using a theta all of a sudden. I meant to put a u. I don't know where that theta is coming from. Some previous course I've forgotten about, I guess. But anyway, sorry. Yeah? Oh, no? Personally, I was asked this question once in my junior level electromagnetism course. In junior level electromagnetism, if you want to talk about the charge density, right? Charge density of a point charge at position x naught, you could do this, q delta of x minus x naught. See how that works? If this is dq, this is, rho is dq dx, right? If I have the integral of rho dx, so q is equal to rho dx, that works, right? That works because when I integrate this, I just get back q again, right? And this charge density, this density function says that the charge density, the charge per unit length, is 0 everywhere except at x naught. So this is the charge density for putting a point charge at the point x naught, right? And in that same electromagnetism course, we did things like the charge density in 3 dimensions is like q times delta. You might put a 3 up here of r minus r naught. And so this right here gives you the charge density for putting a point charge out here in space at position r naught. All right, so the Dirac delta function can be used. It's the mathematical apparatus necessary for writing down the charge density when you have a finite amount of charge at a mathematical point, right? This matters for like physics, for example, 232, because we talk about point charges in there, but we don't talk about Dirac delta functions in there because we have the good sense not to, right? But the junior level course, you can't avoid it. At some point, students ask you, what's the formula for the density of a point charge? And then you have to be honest with them, and you have to tell them, well, it's a Dirac delta function, suitably scaled, all right? And this is really cool because if you integrate this thing over a 3-dimensional shape, the only way that 3-dimensional integral gives you a non-zero thing is if the point r naught happens to be in that 3-dimensional space. That's what the Dirac delta function's for. So for one thing, it's for modeling point charges in electrostatics and things like that. So going back to my question, what do you guys think? What's the derivative of the unit step function? I was buying time for you to figure out the answer. What's that? It's 0, right? It's not changing. And then what happens? It changes from, like, let's instead of doing the unit step function, let's do something a little bit more muted. Like in reality, it's more like this, right? In terms of physical implementation, it does something more like this, doesn't it? This is like a physical u of t minus t naught, which is technically speaking not u of t minus t naught, but it's like a slightly smoother version of it, right? Where I'm taking some particular time, right? I'm taking some particular time, delta t, to actually make the switch from 0 to 1, right? Now if I ask you what's the derivative of the blue curve, you ought to be able to tell me. It's 0, right? Right until it's not. At this point, it goes from 0 up to some large value, and then it decreases back to 0 again, like that, right? Because it's increasing over a small amount, and then it's constant again, right? So what's the derivative of the unit step function? All right, I tried. Infinity? Well, yes, this infinity. So the derivative of the unit step function is the delta. Is how to think about this. Now, I'm not going to make fun of you guys for not telling me that, but my junior level electromagnetism class, electromagnetism professor, I think it was, no, it wasn't Wang, it was Chung, Dr. Chung. He must have been like 5'2", and he could lecture like at the very bottom of the board because he adopted a frog-like posture, which I can best illustrate like this. Like, right there. It's quite something. But he mocked us for not knowing this, because it's so obvious. Like, once you say what I said, I guess. But for me, it was a clash of cultures, because that same semester I was taking real analysis as a math major, a double major in math and physics. And in my real analysis class, I'd been chided for like the most banal of stupid mistakes. So then, oh, you don't know the derivative of a discontinuous function, this infinite non-function? Come on, what's wrong with you? Sorry, I thought it was amusing at the time. Anyway, so the other thing you might think about is something like, I don't know, I need something to smash. So like, imagine you take this, right, and you do something like, oh, hey, there's a magnet in that, what do you know? That's pretty cool. It bounced off there and onto there. I'm glad that we should have been wearing eye protection, apparently. Oh well. Nothing to see here. I guess I might need to edit this video. The point I was trying to make was that the force on the eraser is very short and very large, right? And so you could use a delta function to do something like that. The thing I usually talk about is a hammer, right? If you take a hammer and hit a nail, what happens? So the force of a hammer, you could say something like J times delta of t minus t naught, right? And if that's the net force on the nail, you could say, well, that's equal to dp dt, right? Because Newton's second law in terms of momentum is F is equal to dp dt. And then you see if we integrate the hammer force, if it's hammer time, say from, I don't know, time 1 to time 2, then that gives us what? Well, it just gives us what? We just get J naught. See, so the multiple, whatever number we're multiplying, gives us the change in momentum, right? See, on the flip side, this is equal to the integral from t1 to t2 of dp dt, right? But what's the integral of dp dt? Well, it's p of t2 minus p of t1, right? This is also known as, the change in momentum. right? Sometimes it's also called J, impulse, right? In physics, the change in momentum is called the impulse. So if we had, so this is why sometimes you'll see delta of t minus t naught is called the unit impulse. The unit impulse is another name for the delta function. Because if you think of it as a force, it gives you a unit of impulse. All right? Okay, so these are some reasons you might think about a delta function. Let's talk more about how to solve differential equations involving them. So I guess first order of business, I probably should calculate what's the Laplace transform of the delta function based at t naught. What do you think? I think this is going to be considerably easier than the unit step function, So what happens here? We evaluate. So we do e to the minus s t naught. Then, yeah, there you go. Done. No, it amuses me. Of course, I don't think we almost ever need this, but if you did have a function times the, the delta function at t naught, how would that go? I don't think I ever need this, but let me just get out of my system here. What do? Integration is just evaluation. So we do e to the minus s t naught, f of t naught. So there you go. That's it. So an example I usually do at this point is like a spring mass system, where it's just minding its own business, sitting there, not vibrating at all, and then you hit it with a hammer, whack, and deliver some impulse to it. Then what happens? Well, the spring mass system is then going to oscillate after that time, right? So mathematically, that looks something like this. We'll do a spring mass system without friction just to keep things relatively simple. So we got y prime prime plus y is equal to, what kind of impulse do you want to give it? Unit impulse, 10 impulse units. How many we want to put? We can put any number you like here. What do we want? 12? Okay, 12 it is. And we're going to do that at time, let's do it at time 2 pi. No, I'm sorry, pi over 2. That's more exciting. We'll do it at 1.5 seconds. 1.57 blah, blah, blah seconds. And further context here, just to make things kind of fun to think about, well, if y of 0, y prime of 0, both equal to 0, that makes the problem easier, all right? So the first order, so yeah. Oh no, yeah. Ironically enough, the equations are still true, but yes, thank you. There are other, well, I'll shut up. There's a whole theory of integral transforms that's beyond the Laplace transform. There's Fourier transforms, there's Legendre transforms. There's a whole theory of integral transforms that we're just scratching the surface on in here, all right? But anyway, to really do those properly, you also need complex analysis, which is why it's kind of better suited for a graduate, like a graduate engineering mathematics course, which is kind of like 1/3 linear algebra, 1/3 complex analysis, and then 1/3 like higher methods and differential equations. My wife used to grade that for NC State back in the early thousands. Primarily, she'd have scans of, most of the students I think were in India. It was an online class. So she'd get this like stack of papers like this to grade. It was really something. They did the Frobenius method and everything there anyway, but. So we take the Laplace, so the method for solving differential equations with the Laplace transform is what? We take the Laplace transform, number 1, we do algebra, solve for big Y, number 2, And then we make it pretty, number 3, I lost track. And then we take the inverse transform to get back to the time domain, right? That's the method. So start with, we take the Laplace transform. Laplace transform of y prime prime of s plus the Laplace transform of y equals the Laplace transform, I'll pull the 12 out, Laplace transform of delta of t minus pi over 2. Now I don't usually write down this step, but I decided to do it today. Now this gives me s squared, big Y, plus big Y equals 12 e to the minus pi s over 2. On your sheet, it's a little bit hard to see it, but this is basically, it's really hard to see. Under table 7.2, the 1, 2, 3, 4, fifth thing down says the Laplace transform of y prime prime of s is s squared Laplace transform of f of s minus s f of 0 minus f prime of 0. Now here f is equal to y, and y of 0 and y prime of 0 are 0. So that's why we just have this one term here, right? Okay, so that's it. Solve for big Y. We've got 12 over s squared plus 1 e to the minus pi s over 2. All right, so solving for big Y was kind of easy here. Now we need to take the inverse Laplace transform. All right, so y of t is equal to the inverse Laplace transform of 12 over s squared plus 1 e to the minus pi s over 2. All right. Now we got to go back to last class. We derived some things, right? Do you remember what we derived? We derived like the inverse Laplace transform of big G of s times e to the minus as, I think it was, at time t is equal to little g of t minus a times the unit step function of t minus a, where, of course, as usual, Laplace transform of little g is equal to big G. So my big G is 12 over s squared plus 1. What's the inverse transform of 12 over s squared plus 1? Well, it's simply 12 times the sine of t. But I don't do t here, I have to do what? Right, my a here is pi over 2, right? So I do t minus a, t minus pi over 2. There you go. That's what happens. That is the equation of motion. What goes on? Can we graph it? So the spring mass system's just minding its business here. I'll do time this way, up until time pi over 2, right? It's motionless, sitting there in the equilibrium position, yeah? And then we whack it with the hammer, and then it just starts this deal, right? And because this is a spring mass system without friction, it just keeps oscillating forever and ever, yeah? Notice that the motion's continuous. Do you see that? Before and after, if you're a little bit before time pi over 2, x is equal to 0. And if we're just ever so slightly past time pi over 2, we're still really close to 0. Because sine of t minus pi over 2 starts out at 0. It's just, this is just the graph of sine t shifted pi over 2 to the right. Right? Times 12, of course, but any questions? No? All right. Let's see here. Now, if you compare the trouble of this versus the trouble of solving a differential equation which involves the unit step function, this is way easier. Way, way easier. Check this out. So example 2, we could try to solve, oh, I think I already did this one. I didn't do exactly this one, but I guess it doesn't hurt to do it. I'm just going to show you this example, and you can take it or leave it, but my apologies that this is slightly similar to what I did last time, but I think this one's easier, so maybe that's a good thing. This time we'll have y of 0, 0, but we will make y prime of 0 equal to 1. All right. Let's find the solution here. All right. Find the solution. Now, so first order of business, we take the Laplace transform. We get s squared times big Y minus s times y of 0 minus y prime of 0. That's all from the y prime prime term. That is the inverse Laplace transform, excuse me, the Laplace transform of y prime prime. These three terms. All right, that's this. Now we have minus 2, parentheses are your friend, s times big Y minus y of 0, close parentheses. I will color code this for you as well. My apologies in advance for the hideous Carolina blue. There we go. Or whatever this is. I don't know. And then, of course, the Laplace transform of y is big Y. So plus your big Y. Now, what was the Laplace transform of the unit step function? Do you guys remember? It was 1 over s, e to the minus s, I believe. Is that on the sheet? It should be. I think it's basically it's written by hand, right under like equation 8. It's on the far right side of the sheet. Do you see it? Laplace transform of unit step function t minus a of s is equal to 1 over s times e to the minus as. Do you guys see it? Yeah, it's right there. Yeah, so then, okay, so let's see, we got ourselves an s squared minus 2s plus 1 all times big Y is equal to, let's see here, 1. Yep. Plus 1 over s times e to the minus s. All right. Then this gives us big Y is equal to 1 over, that's actually s minus 1 squared, isn't it? Plus 1 over s times s minus 1 squared e to the minus s. Doing the algebra. So there are two parts here, and we should think of them separately. There's no need to do everything at once. We'll think of these as two pieces, all right? So this is piece number 1. This over here is piece number 2. All right? So piece number 1, I can just take the inverse transform of that immediately, right? The inverse transform of 1 over s minus 1 squared is simply t e to the minus t. Excuse me, t e to the t rather, right? So like this first piece just inverse transforms to t e to the t, I believe. Yeah. The other one I need to think about. So we're going to need to do something called partial fractions here, right? Important point of order, do not, I repeat, do not include the exponential term in your partial fractions. There's no quicker way to communicate to me, I'm not done studying this material, I certainly don't deserve an A on this test, than to do this. Like, put the exponential into the partial fractions. That's your way of telling me I haven't finished studying, right? You won't do that on the final. Of course, everyone won't do this on the final, but some of you will do it on the next test. Don't do that. Actually, you guys are here, so probably you won't do it. But anyway, so A over S plus B over S minus 1. But it is a time-honored mistake to include the exponential in the partial fractions and then get really, really confused about it because the constants, A, B, and C are constants. And if you try to put the exponential in there, it just doesn't work. Okay, it's not supposed to be there. This is a rational function in S, and it does admit a partial fractions decomposition. The moment I put the e to the minus s in here, it all falls apart. All right. Anyway, so don't do it. Now, to get this, I recommend we put maybe s equals to 0, and then maybe put s equals to 1. Oops, my bad. What did I forget to do? One more step here. So this is 1 is a times s minus 1 squared plus bs times s minus 1, and then plus cs. All right. With that, multiplied by the denominator, now I set s equals to 0. Lo and behold, I get 1 is equal to a. So, okay, 1 is equal to a apparently. That's good. But s equal to 1, I get 1 is equal to, well, that's 0. That's 0. I get 1 is equal to c apparently. So, yeah. I guess we got a and c. That was, now solve those equations. Answer to solving those equations is yes, right? They're already solved. But we do need to know what b is. What should we do? What should we do? Pick any number. I heard pick any number. That's almost true. There are two numbers that I won't allow you to pick. 0 and 1. Anything but those, right? Yeah, so s equal to what? What do you want?
2.
I heard a 2. I like a 2. 5 is 5 is just not cool. Not cool, guys. Not cool. 1. No. So s equals to 2. 2 minus 1 is 1, so that's a. And then 2 times 2 minus 1, so that's plus 2b. And plus 2c. But of course we know that that's actually 1 is equal to 3 plus 2b, right? So 2b is actually equal to minus 2b, minus 2. In other words, b is minus 1. Yay. All right. So now that we have done the requisite algebra, let us write down the fruits of our labor here. Y of s is in fact equal to 1 over s minus 1 squared. Nothing changed there. But now, big old parentheses, we got ourselves a 1 over s. Great. Minus 1 over s minus 1. Right. Then, oh yes, plus c, plus 1 over s minus 1 squared. All right. Great. And that's all times e to the minus s. All right. So now we have everything we need to write down the answer, assuming we understand how to implement equation 6 in the translation in T theorem. If you look in your sheet, if you look at like equation 6 under the translation in T under the theorem 8, you see that? That's really what we're using. I wrote it with g here. The inverse Laplace transform of g of s times e to the minus as is that. I mean, we have to use that theorem. All right, so here we go. Y of t is the inverse Laplace transform of big Y at time t. All right, so we'll start out with the first piece. The first piece is easy. That one's free. That one's just t e to the t. That's just a basic Laplace, inverse Laplace transform. It's on your sheet. Now, I'm going to do plus, let's see here, parentheses, u of t minus 1. So I'm thinking of this piece right here, guys, as g of s, all right? So as a in-between step, I want to write down what is the inverse Laplace transform of g. G of t, inverse Laplace transform of just g of s. What's that equal to? The 1 over s is equal to 1. Remember the Laplace transform of 1 was 1 over s. That was one of the first things we did. Minus e to the t. The Laplace transform of 1 over s, inverse Laplace transform of 1 over s minus 1 is in fact e to the t. And then this guy plus t e to the t. All right? So that is g of t. Now g of t does not go here. What goes here? G of t minus 1. It's a matching set. Whatever you've got in your unit step function, it also must appear in the arguments of the g. And so here, that just looks like 1 minus e to the t minus 1 plus t minus 1 e to the t minus 1. All right, and there you go. Solved. This is the solution to the differential equation. The way this works is at time 0, the response to the given initial conditions is simply t e to the t. And then once the unit step function turns on, the system responds, and as such, this is the response. Right? If it was a homogeneous problem, if the the unit step function wasn't there, the solution would just be t e to the t. This red part is, again, because we put the inhomogeneous unit step function in. All right. Any questions? All right. Let's see here. Well, oh. Yeah, and so this is kind of representative of the difficulty. If you have a quadratic differential equation, you make a second order one, right? And if you have a unit step function, if you think through the algebra, you're going to end up with a cubic in your denominator, right? So in order to take care of that, you're going to have to do partial fractions with 3 parameters and work through it. Like that's how these go. In contrast, example 1, if you have a delta function, you just solve for big Y and you're done. All right. I think I've got some more examples for you guys. See if I can find one. All right, so get that. So sometimes, I don't think I have anything in your homework about periodic functions. There are things to say about periodic functions and Laplace transforms, but I don't think anybody else is covering them, so why should I? One kind of fun one to talk about, at least a little bit. I do think I had something in your homework of this nature. I'm not completely sure I did, but I was thinking about putting it in your homework, whether or not I did. Which is to say that we can extend the discussion of Laplace transforms to like series. And like you can take the Laplace transform of a series and have a series. You can go from a series in T to a series in S. These kinds of calculations are possible, and sometimes that's kind of like the only thing you could do. Like for example, what example am I on here? 4. I guess 3. So here's a function you might not have thought much about. F of t equal to, here's the deal, sine of t divided by t for t not equal to 0. Well, let's say for t positive. Let's keep it simple here. And 1 if t is equal to 0. I mean, I guess I could just let it be not, fine, I'll just stick with the notes. Fine, whatever. It doesn't really matter. We're going to calculate, I want to talk about how to calculate the Laplace transform of this. So if you think about calculating the Laplace transform of this directly, it's rather unpleasant, right? Because you'd be talking about integrating what? Think about what you'd have to integrate. You have to integrate exponential e to the minus st times sine of t, all divided by t. Just checking on my audio. So you really don't want to do that. But it turns out that this function has a relatively nice power series representation. You see, because 1 over t times sine of t, right? This is 1 over t times the sum, n equals 0 to infinity, minus 1 to the n, divided by 2n plus 1, factorial, t to the 2n plus 1, right? And as such, we can rewrite this as the sum, n equals 0 to infinity, minus 1 to the n, over 2n plus 1 factorial, t to the 2n, yeah? And like, what is this? If we write it out, we're talking about what? Like t minus 1/6 t to the 4th plus dot, 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 all right? Here's the interesting thing, is that power series, right, is exactly equal to f of t. This right here is literally equal to f of t, and the cool thing is, it even works when t is equal to 0. Because if you plug in times 0 into the power series, oh, my bad, I don't know how to do math. Is it t that it starts with? No. I should be, I'm sorry guys, this is what I should be doing, right? The sine series starts with t, and then like minus 1/6 t cubed, right? So what should I have here? I shouldn't have this and this, right? What should I have? I should have 1, right? And I should have t squared. Yeah, sorry about that. But my point is that if you plug in t equal to 0 into that series, you just get 1, right? So this function is what's called analytic. All right, so anyway, the point is, if I wanted to calculate the Laplace transform of f of t, right? Here's the cool thing, is you could do it like this. You could say, oh, well, that's the Laplace transform of the summation, n equals 0 to infinity, minus 1 to the n, over 2n plus 1 factorial, t to the 2n, all right? And because the Laplace transform is linear, and because it plays well with the convergence here, which I won't prove, but I'll tell you it works. What is the Laplace transform of t to the n? Well, I don't know, let's figure that out next, right? T to the 2n. Now, do you guys remember we worked this out the other day? What was it? What was the Laplace transform of t to the n? How'd that work? I mean, instead of using n, let me say Laplace transform of t to like j. What would that be equal to? I remember it was 1 over t to the j plus, my bad, t, listen to me. 1 over s to the j plus 1, right? But there's a factorial. Where did it go? Upstairs? And was it j plus 1 factorial, or j factorial? We could check. It's on the sheet, right? There it is. Third one down from the top in table 7.1, the Laplace transform of t to the n is n factorial over s to the n plus 1. There it is with j. So this is the sum, n equals 0 to infinity, minus 1 to the n, divided by 2n plus 1 factorial. This is going to give us 2n factorial divided by s to the 2n plus 1. Right? Which, of course, we could simplify a bit, right? This is actually what? These guys be canceling, right? And that's as far as we go. All right? The point is the Laplace transform of a series in T will give us a corresponding series in S. It's not a power series. What is this, by the way? Not a power series. Rather, it's what's called a Laurent series. A Laurent series is a series formed by possibly reciprocal powers of the variable. You can also throw in like positive powers. It would still be a Laurent series. Like generically speaking, a Laurent series has the following form, guys. It's like the sum, like minus infinity to infinity, something like am, x minus x naught to the power m. This is a Laurent series. So it's like a power series plus reciprocal terms. This is a Laurent series. This is a big deal, an important problem, kind of object to study in Math 331. If you take complex variables, we study Laurent series and their interaction with integration. It's actually a very interesting story, but one that I shouldn't tell here. All right, there's that. So there's another lingering issue that we should settle today, which is, what about like square root? What's the Laplace transform of the square root of t? Or cube root for that matter, right? So that we have not discussed yet. We've only talked about really integer powers, all right? And so to understand this, we need to talk just a little bit about the so-called gamma function, all right? So definition, the gamma function, which is called capital gamma of t, is defined by gamma of t equal to integral 0 to infinity of e to the minus u to the t minus 1 du. That's the definition of the gamma function. We can show by integration by parts that gamma of t plus 1 is actually equal to, as it happens, t times gamma of t. All right? This is an identity which is true for the gamma function. And you can also calculate that like gamma of 1, we can show gamma of 1 is equal to, well, we can just work this out. What's the integral from 0 to infinity of like e to the minus u du, right? So we were talking about minus e to the minus u evaluated from 0 to infinity, also known as like, minus e to the minus infinity plus 1. Don't tell the math professors I wrote this, of course, but e to the minus infinity is also known as a 0. So this works out to 1, all right? So what this means then is we have a theorem. We can argue, in fact, that gamma of n plus 1 is equal to n factorial. Let's see if this starts right. Let's check on this. What happens if I put in, what's 0 factorial equal to? It's equal to 1, right? Is that equal to gamma of 0 plus 1? Well, that's gamma of 1, which is equal to 1, right? Hooray. So that's a good start. And how about what's the other defining, how do you define the factorial? The factorial is defined as such, right? N plus 1 factorial is equal to n plus 1 times n factorial for n in the n equals to, let's see here, 0, 1, 2, et cetera, right? We've already defined 0 factorial as 1. This defines 1 factorial, 2 factorial, 3 factorial, and so forth in terms of 0 factorial. And so, you know, this is the recursive definition of the factorial function. And so, like, notice that if I use, words. So this would be equal to, allegedly, sorry, I'll get it to eventually here. No, so this would be what? In terms of gamma, this would be gamma of n plus 1, right? And this would be, well, that would be n plus 1, right? But a property of gamma is that this is equal to what? So I'm doing this thing right here with t plus 1 playing the role of t. So whatever's here, I add 1 over here. So I think this is supposed to be n plus 2, right? Which is also known as gamma of n plus 1, right? Which puts us in contact with that. All right, anyway. Trust me when I tell you, there have been semesters where I have gotten very, very confused about this business. So let's just, it worked. Let's just let it be there. This is the main thing, that this, so what the gamma function is a continuous extension of the factorial. All right, and so if we calculate the Laplace transform of, t to the power n, what is that? Well, that's the integral from 0 to infinity of e to the minus st times t to the n ds, right? If I change that from an s variable to a u variable, what's this look like? Oh, my bad. T to the n, huh? Oh, there's still something else I'm forgetting. Uh-oh. Oh, that's right. There is a substitution that we must do in order to bridge the gap between these worlds. It's not just a simple relabeling. It is more interesting than that. So sorry. Let me do it over here. So here is the calculation. This is page 140 of my handwritten notes. I may or may not have typed this up yet, guys. I don't remember at the moment. I'm sorry. But the Laplace transform of t to the n of s is the integral from 0 to infinity of e to the minus st. So we're just right where I was a second ago here. I just erased it. But then here's the sneaky step. Let u equal to st. If we do that, then du is s dt, and t to the n is u